black box geometric computing with Python course, from theory to practice. If you want to see the course notes and all the material for this course, please check it at the URL in the slide or in the comments below. So this is a course presented by Sebastian, which works at TU Berlin, and Teseo, Chencheng, and me, I'm Daniele, from New York University. The goal of the course is to teach you how to design, program, and analyze algorithms for doing geometric computing. And in particular, we will give you hands-on experience with shape modeling and geometry processing algorithm by, during the entire course, showing you live demos. And you will see in a second that you can also access the same material and run it on your machine as you follow the videos in this course. And a focus of the course will be on learn how to do batch processing of large collection of geometric data to use it for deep learning pipelines. First of all, what is geometric computing? It's a field that is in between discrete differential geometry that focus on representing surfaces and volumes and defining the operators that work on them, numerical methods for solving partial differential equations with a specific focus on accuracy and reliability of the solution and to work on complex geometries. High performance computing to allow us to compute our result in reasonable time, in particular taking advantage of vectorized computation and GPU acceleration, and a part of human-computer interaction, because the algorithm that we expose needs to be used by people that don't have necessarily a technical background. And so it's a question of also how do you expose these interfaces to edit or work with 3D geometry to users. Geometric computing is somewhere in between all these fields, and especially now it has to deal with large collection of data, which is something new, but at least in our community has only been started to be studied recently. Geometric computing involves the entire life of a shape or the entire process that a shape goes through, starting from the real world when you have a physical object and then you acquire it. To get, for example, a set of range images that are 2D images where for every pixel, instead of having a color, you have a depth. These range images are then converted, consolidated in an unstructured model. In this case, it's a triangle mesh, which is going to be the main focus of this course. And then, depending on the application, this mesh is converted into a structured one. Then, meshes are used in a large list of applications, such as computer animation, physical simulation, fabrication, visual effects, or structural analysis. And in particular, there is a specific interest in geometric computing for fabrication, where the goal is to optimize geometries that are then going back to the real world thanks to 3D printing to produce a variant of the original object. So the tools that you're going to study in this course are going to be useful for all these different steps, and they're going to be building blocks for creating algorithms for all these different steps of this pipeline. In this course, we're going to start by introducing a finite element method from scratch. And then we are going to move on black box analysis that is going to cover how do you start from geometry and how do you solve partial differential equations inside them. And we will see that these tools are very convenient for geometric computing, and this will be covered in the second part of the course that is going to be more applied, where we're going to go through many algorithms for geometric computing that are available in libigl, and then there are going to be two major applications, one in geometric deep learning on how to generate the data sets and use it for training a network, and then the generation of meshes and numerical simulation targeting scientific computing and mechanical engineering applications. And then there are going to be some concluding remarks. So let's get started. The first thing is to install all the libraries that you will need for this course. So the libraries that we're going to use are implemented in C++ for efficiency reasons, but they're all exposed to Python to make the integration into other softwares easier. Through Conda, so you can install it with these 4 lines. If you don't want to install it on your local machine, what you can do instead is use Binder. So I'm going to show an example here. So if you go to the website of the course and you go to course material, you're going to find the notebooks, and in particular there is this binder icon here that allows you to launch the corresponding notebook on another tab of your browser. And when you go here, you need to wait a little bit to get the repository running, and after it runs, you can directly execute in here live the commands that are going to be used in the slides used by all the instructors of this course. Let's go back to our slides. What libraries are we going to cover here, and what do they do? So one comment before we delve into it is that you should be able to run this course on Windows, Mac OS, and Linux. And if something doesn't work, please do let us know either via email or opening issues on GitHub. So the first library is Meshplot. This is a library integrated with Jupyter Notebooks that allows you to visualize 3D data. And you will see during this course that it can visualize many different things like surfaces, signal on surfaces, vector fields, and annotations. And all of these is easily callable from Python, mostly requiring just a few lines of code. Another one is libigl. This is a library that has been developed for many years. It contains a large collection of geometry processing algorithms, and we're going to use extensively this library for doing both loading of meshes and processing, and there is going to be an entire section dedicated to libigl. Then wild meshing. This is an open source library for doing meshing, so for both triangle meshing in 2D and tetrahedral meshing in 3D. It's also this one fully available through Conda, and you're going to see in one of the applications how to use this library to generate your meshes. Finally, PolyFEM. This is a library for doing finite element, for doing simulations using the finite element method. And also this one is available through Python, and it will be used in one of the applications. So before we move on to the technical part of the course, I would like to just give an overview of what is the major similarity between all these libraries and everything that you're going to see in this course. And this is a standardized way of transferring data and representing data so that it's possible to move it between different libraries in a seamless way. So let's start with a basic representation for surfaces that we're going to use, which is a triangle mesh, meaning that the surface is divided into triangles, and so it's sampled at a set of points, and these points are connected with triangles. So let's zoom in here. And so now if you look at one vertex, this vertex will be described by X, Y, and Z coordinates. So we have one set of coordinates for every vertex. And the way we decide to represent all of these is to take all these vertices and put them all together in one matrix that has as many rows as the number of vertices and 3 columns, one for all the X coordinates, one for Y, and one for Z. So this is just a n times 3 with n the number of vertices. It's a matrix of real numbers. Now let's go to the faces. So every face is made of 3 vertices, and we're going to identify it by storing the 3 indices of the vertices. And in this case, the orientation matters. We have a convention that using the right-hand rule, we want this vector to point outside the surface so that we fix this orientation consistently for all the vertices of a mesh. So after we have these, we're going to have many faces to store. And so for every face, we have a set of indices. And so similarly to what we did before, we place all these indices in one single matrix that has size m times 3, where m is the number of rows and is the number of triangles. And we have 3 columns, one for every one of the indices. And so now the entire mesh is represented as two matrices, one that stores the coordinates and one that stores the indices into the matrix of coordinates. So why do this? Like, why using just raw matrices to store the data? So there are many reasons for this. One is that it's memory efficient and cache friendly. This is a very simple representation. Every time you read a number, you're gonna read a few, all the one that fits in your cache line. And in this case, it's gonna be a few numbers that are actually useful for subsequent computations. Um, one major practical advantage, practical from a point of view of people developing algorithms, is that indices are so much easier to debug than pointers. So in our case, when you have these two matrices, you can just plot them in a terminal for a small match, and you can look at them and you can make sense of it. Since they are simple, they are trivial to copy and to serialize, meaning that most libraries use matrices, and so as long as you use a standard format, it's very easy to save a matrix and load it somewhere else. So this makes our algorithm interchangeable with many other libraries. For example, if our decision for this course is to use NumPy as the common denominator for exchanging data between different libraries, and this allows the libraries that you saw, like libigl and PolyFEM and wild meshing, to directly be usable in an application written in PyTorch and directly exchange data with it, because all the data is represented in NumPy format. Or similarly to TensorFlow, or if you want to use some function in SciPy, or even externally to Python, you can save it to a file and load it back on MATLAB or do some processing with OpenCV. So this concludes the introduction, and we are now going to continue with an introduction to finite elements.